I'll start the recording. So section 3.3 deals with, it's more than this. Hold on. It's, I have to fix that title. It's modeling with, hold on, I got to get that title right. It's modeling with systems. Modeling with systems of first order differential equations. Now, hold on here. Hold on, where is it? Okay, so, you know, what would sort of a natural system be for like a system of differential equations? Well, one can think about a predator-prey model. Section 3.3 is going to have a variety of systems of differential equations. But like, for instance, you could have an interconnected system of tanks, and that would form a system of differential equations. They have good examples in the book, but I'm focusing here on the predator-prey model. So we have here a dx dt and a dy dt, where x of t and y of t are measured in thousands. And based on that differential equation, we want to think which variable is for prey and which is for the predator. Okay, which variable is for the prey and which is for the predator. Okay, so let me give you a moment to copy it down. Make sure you're all good. All right, so let's see. There is some input here. Well, you know, Michael's thinking about it. Let me ask you this. Let me ask you this. If x equals 0, if x equals 0, then dy dt would equal what? If x equals 0, what would dy dt equal? And I see some interesting comments here. It would equal 0.2 times y. What kind of growth does this differential equation represent? Dy dt equals 0.2 times y. Antonio, you're right. Y is the prey, but this differential equation represents good, Michael, exponential growth. So I appreciate all responses. Yeah, if x equals 0, the second differential equation would be dy dt equals 0.2y. And so in the absence of predators, we know prey are going to grow exponentially. So this then tells us that y is the prey. Okay, and x is the predator. Let's see, Matthew, let me see yours. Now Matthew's saying predators x. I'd have to think about that a little bit, Matthew. I like to think like this. What if y were equal to 0? If y were equal to 0, then dx dt, sorry, I'm going to write it. If y equals 0, then dx dt, maybe I'm not, hold on, I'm over here now. So now I'm looking at the first differential equation, and I'm saying, what if y equals 0? Then dx dt equals, good, negative 0.1x. Trying to write this the best I can. All right, and so is that exponential growth or exponential decay? If y equals 0, then the first differential equation becomes dx dt equals negative 0.1x. Would that mean that the population of x is growing or decreasing with time? Decreasing. Good, good, right, Ann, thank you. So that means then, well, we know if there's no prey around, the predators are going to die out. So it makes sense that y is the prey and x is the predator. And what we want to do in this problem is we want to graph these two. There's a connection. Obviously, there's an interdependency between prey and predator. So how would we graph these two solution curves? We would use MATLAB. Let me show you real quick how to use the MATLAB. Okay, so if you go to a Blackboard here, just go to. This will only take me a moment. I know we're at the end here, and I'm going to get your grades. I'll show you the grades, but just one moment. So if we go to course information here, go to. Can everybody see the Blackboard? Okay, on the screen. Okay, thank you, Thomas. Thank you. You go to MATLAB Programs, click here, and then here is for section 3.3. This MATLAB program will help you graph solution curves for prey and predators. Okay, and so what you do is you run the code. Okay, one moment here. You click on the link, it'll bring up the MATLAB program. You download it and paste it into your viewer in MATLAB. And let me make this, hold on here. Let me show you here. Here we are. There we go. There it is. There's the program. And it goes with exercise 11, section 3.3. So what we'll do is we'll just copy and paste. I start out with clear vars to clear any old variables in my workspace. Copy and paste, and then I get a graph that's produced. I get a graph that's produced. Hold on here. And in terms of I want you to study this program on your own, and you will get an idea of why the numbers are where they are. You know, the initial, I'm going to graph time goes from 0 to 100, and initial conditions are 6, 6. And we're using the command called ODE45, which is MATLAB's Euler's method. Okay? And when you when you get your graph, I'm almost done here. Thank you for your patience, everybody. Hold on. Where is the doggone graph? Where is the graph? Hold on. I just had it. I just had it. Okay, this is what I want. This is the graph. All right, so let me try to bring it up here. Here we go. This is the graph you'll get. Okay, and so I'm going to let you, so you'll be working for next Tuesday's homework. You'll have some problems some different problems, but in terms of using a MATLAB program, you'll be working with some problems like this, predator-prey type models. Are there any questions? All right, I'll stop the recording.